Hi, my name is Jeremy Linton. For the past few years, I've had the opportunity to be part of ARM's distro team. Our mandate is to work within the larger open source communities to ensure that ARM-based machines and ARM-specific architecture features are enabled and work as transparently as possible for our partners and their end users. In my case, I've been focused on server platforms and Red Hat-specific technology stack. And as a result, when I'm not backporting things, I'm a drive-by patcher of various projects and kernel subsystems. Today, I'd just like to talk about some of the work we were doing making the RaspberryPi SystemReady, which is a certification that ARM provides for assuring that the platform will work out of the box. So I'd also like to talk about the challenge many people have commented on in the ARM ecosystem, the lack of what in other ecosystems are considered general purpose machines that can be purchased standalone and through the choice of OS, software, or hardware choices put to work in various one-off or fairly low volume markets without employing kernel or firmware engineers. The desktop laptop market is currently cited, yet the problem exists in the commercial space for long tail of devices like intrusion detection appliances, digital signage, consumer NAS, and others. On the other hand, I would claim this also results in an engineering problem where ARM-associated devices are filling up the Linux kernel and other operating systems with one-off drivers for what should be generic industry standard devices. So how much code do I have to write to support a cooling fan given one SoC, 3 boards, and 4 OSs? And one of the entertaining, or not so entertaining, as I commented earlier, points about all this is a standard SDHCI driver has a couple dozen variations in the kernel, and a fair number of them are due to power and clocking quirks. So Steve Jobs says the way you get productivity is not by writing more code, it's by writing less. So just a bit of overview what we're talking about. How do we fix some of this fragmentation? And how do we get to just works, and some thoughts behind System Ready, what modern ARM machines look like, the proof of concept Raspberry Pi, and some examples that come from that project, along with some of the work in the UEFI space and ACPI, what's going on with DSD and DSM, which are the properties, the ACPI properties for method calls and device specific calls, and some credits about the fact that this project has been a community effort. ARM has been very successful in the build-to-order, high-volume, single-purpose device space, and yet ARM machines have been evolving. The ecosystem has a number of really strong points: flexible implementations, creative cost-cutting, ecosystem diversity, broadly scaled, and these one-off devices work well for traditional embedded space. Frequently, they're not network connected, so there's not security issues directly on the internet. But what's happened in the last decade is these machines have moved up the food chain. They're now 64-bit. The CPU manual has, exploded along with the hardware complexity. It's now about, a little over 8,000 pages. And so this has also caused boot flows, explosions, security modes. And we're now running general purpose operating systems, which themselves are large and heavyweight. And for example, there's about 3,800 kernel modules that ship in Fedora for an ARM machine. And so what we really want is an ecosystem that just works. Engineer ready is not an option for many of these markets. And so we're at the point where the next logical step is that the hardware platforms that aren't deeply embedded or built for a particular part of the consumer electronics market really should be looking to support the same set of generic OS distro ecosystems one would expect of any other hardware platform. Yet today, few of these ARM platforms can switch between the software stacks provided by these organizations. And that is a problem because a lot of them want to focus on their particular value add rather than maintaining an OS. The solutions aren't frequently helpful if they're Linux only either. So this turns out part of the ARM ecosystem that has already solved this problem is the data center. Through the past few years, long road of SBSA and SBBR, which is the server-based systems architecture and server-based boot requirements, have shown that the platform standards can work with the ARM-based machines. But along the way, the focus on servers has meant that this part of the market is borderline build to order as well. And so the there's been two primary steps of solving this, right? Which is we standardize either the hardware, so that uses industry standard, XHCI, NVMe, PCI, as well as the software firmware side. So all of this, it pretty much is a drop-in replacement for existing servers. And so what happens when the hardware doesn't work? Do you respin it or cork it? And most of the answer usually in the server space has been you respin it, and this has caused a lot of lost years and hardware vendors that have given up, because it turns out that getting all this hardware exactly right the first time around is a little difficult. And yet, there have been a number of successes, and this continues to gain ground, with hyperscalers and HPC. But these are really high-end parts generally. People aren't putting 128 core machines on their desktops with 16 DDR channels. So in the mid-range of the ecosystem, we have a lot of repurposed devices which come from phone SoCs, set-top boxes, various laptop form factors. And how do we extend this ecosystem that just works to other parts of the ecosystem? And one of the problems has been that there's no user installable operating system support as well, right? The vendor ships a BSP, and maybe it's Linux with a particular kernel version, but you don't get Windows or any BSDs out of the box. And so let's step back for a moment and consider that ARM CPUs have 4 exception levels and 2 security states. That means that Linux and other OS's view of the system is actually fairly limited with modern ARM v8 devices. It can really only see the non-secure EL2 and lower processor levels. Firmware, which is frequently operating system, open source, controls much of the secure processor state. So here we can see that the light blue is what a traditional operating system or hypervisor would see, and the rest of it is already firmware on the machine. But it's not just the main core. Even all but the most trivial designs have some kind of management processors associated or integrated into the SoC for early boot, power and thermal management. And that's not counting all the invisible cores associated with the various accelerators or IO adapters that are also built into the SoC or attached via PCI or USB. And so what we can see here is just like a couple of ARM's reference designs. On the left is Juno from about 2004, 2005, where there's a system control processor, which was little Cortex M3. And a more recent design is the Neoverse N1 software development platform from 2 years ago, which also has SCP on it. So given all that, it seems we have plenty of capability for providing generic platform abstraction. Is it then possible to define a fairly minimal set of hardware requirements and get ourselves at least part of the way towards our goals? If we start looking at these standards, a fair number of the software standards are really just generic abstractions. We have PSCI abstracting all the details of powering a core and ensuring the right caches are active. We have UEFI standardizing the boot sequence. And so this is really just like a separation of concerns. What we want to do is we want to have a baseline platform that's been abstracted so that we can abstract the operating system from the hardware to a certain extent. And when we start looking at it, we look for like a minimal hardware requirement. What is actually necessary that we need in order to boot the machine in a bare bones mode that's not required, that we can layer on additional functionality to expand the capability of the machine. So we just look at, we have a core requirement, we have an interrupt control requirement, standard timers, a couple standard storage controllers. But the bottom line is less hardware that we dictate, the more flexibility we leave our partnership. But we still must balance what can be abstracted and still provide a generic platform target. And so ACPI sort of looks like a logical fit here. And it plays a big role in this abstraction since it removes the need for a lot of the clock, power, thermal controls and drivers that we end up putting in the kernel to individually control some aspect of the SoC. As previously noted, the model of having the AP micromanage everything really doesn't make sense if the platform has dedicated processors monitoring temps, device utilization, and controlling the actual power and clock. Rather than trying to describe a bunch of hardware that may only be visible to the secure world or an external management processor, Giving Linux the ability to set power perf policies and let other parts of the system handle the details simplifies what needs to run in a given kernel. And it's not, so you can also share this functionality across operating systems, right? It's not just Linux, you get the same functionality in Windows, say. One of the nice things about ACPI is it doesn't dictate whether the implementation is on the application processor, running the operating system, the management cores or BMCs. It's all just a question of where the engineering and design is focused. And so a lot of these traditional machines have been DT, and what we end up doing with that is just describing piles and piles of relationships between the hardware versus ACPI in this case, which is dictating behavior, but not implementation. So we could try to abstract DT, which is SCMI, which is a system control and management interface, which extends DT to add runtime services. And it's much of what was actually lost when DT was abstracted from open firmware. So while ACPI is a bit of a mess, SCMI still has two major problems. It's not fully defining concrete behaviors, and it's not gained widespread support outside of the Linux community. So these are the two strong ACPI points, or strong points of ACPI. There are a couple thousand pages of concrete use cases, and it's already supported by Linux, Windows, etc. Oh, and so when we start looking at this, the Raspberry Pi is an obvious platform, right? It's readily available. It's sort of an educational platform to begin with. It's not particularly well documented, but a lot of the core functionality has been documented or reverse engineered by various parties. And so one of the frequent excuses we hear, and it applies to the Raspberry Pi, is none of this can work because our hardware doesn't support, this, that, or the other behavior. So a dozen like-minded individuals representing the common OSs got together about 2 years ago and decided that a better way to prove that this was possible was to pick a problematic piece of hardware and see how far down the path of bolting UEFI and ACPI we could get. And so if we look at the Raspberry Pi, it's full of interesting quirks, legacy DMA range constraints, misaligned register access issues. The PCI is not coherent. It's got a non-standard MSI region. There's nothing on it is, of course, coherent. It's got two different broken SDHCI controllers, which are broken in different ways. The CAPS registers aren't provided. The DMA, at least on some of the older SoCs, has got an interesting quirk requirement. Platform doesn't have an RTC. And of course, the Raspberry Pi Foundation has invented a large part of sort of what one would consider, ACPI's domain by providing a proprietary power clock mailbox interface. And of course, it's been cost optimized considerably to reach its price target. So it doesn't have a lot of things, including a dedicated SPI for, say, runtime UEFI runtime variables. But it does have SPI on it, depending on which one you have, SPI flash, depending on which one you have. It's possible that we will use that there. We have an example implementation with the UEFI runtime variables that are being persisted to flash, as opposed to the normal thing we do, which I'll get to in a moment, which is we persist them back to the firmware image on SD. So the initial strategy, just sort of as a bootstrapping or early bring up, was hide everything that doesn't work. And there's one on the RPi 4 standard platform device, which is XHCI, which, because it's USB, you can plug pretty much anything you want into it. It'll be suboptimal in some cases, but we can plug our storage, our networking, our keyboard, mouse, sound, everything else into it in order to bring the platforms up. And since there's DMA constraints or DMA limits on like the PCI, which is another one of its quirks, we'll just basically limit the RAM on all the devices to 3 gigs out of the box. And so with that, we have minimal ACPI tables. We're trapping to ARM trusted firmware at EL3 to handle some of the mailbox interfaces. Set up a flat frame buffer in UEFI. Reuse. There's an existing EDK2 port for the RPi 3, which I should mention, which was done by various other community members, some of which are actually active in this as well. but it's TT. And so we can reuse the AirSand driver for that. And of course, the EFI variable store, which I already mentioned, we write the EFI variable store back to the EFI image on SD or USB, depending on where it's at. But that only really works when UEFI is in control, because the operating system will take over the underlying SD or USB device. And so we'll get to that. But remember, this is just step one. This is like, 2 years ago, what we did just to see if we could get it to the point where we could boot common operating systems in sort of a bring up mode. And so actually at that point, most ACPI SBSA OSs will boot. You can boot the installers because the graphics you get, via UEFI frame buffer, you get USB keyboard and mice, networking by a USB NIC. We can use a SATA SSDs connected via USB 3 bridges. We get serial debugging via PL011 UART, which is actually normally used for Bluetooth, but you can redirect it. And so there's, at this point, they'll boot, but there's not a lot, there's a lot more to be done. So we just get started, which means now we start adding Genet support into various operating systems. There's Linux patches, which were merged a year or so ago. We fixed the Wi-Fi Bluetooth, which actually mostly worked as soon as the SDHCI started working in the operating systems. And as we progressed, I don't know, earlier this year, the SystemReady program started to come out, and the SystemReady program uses the UEFI ACS compliance suite, among other things, to validate that the machine is complying with the firmware standards. And so this platform was early on selected as a potential target for one of the early release announcements of SystemReady, and we actually ran the ACS tests and the SystemReady compliance suites and corrected the half dozen things that it pointed out, and we ended up with SystemReady ES compliance. And so various other things have been done. CPU frequency control is done via CPPC, which is part of the ACPI specification, and it basically is trapping to EL3 and then calling the RPI mailbox to change the frequency. The system topology tables were set up, PPTT, which is another thing. There's some very basic thermal zones, which we'll see in a moment, an example, because it's fairly trivial to do this stuff. We don't need drivers in the operating systems to monitor temperatures and associate the thermal zones with particular devices or CPUs or just the SoC in total. And we get a whole bunch of things for free, right? Because they're part of EDK2, which is what this is based on, which is an open source UEFI implementation, I guess originally by Intel, but they've sort of relaxed their iron grip over it. And there's a lot of, the community has been growing. And so, we get PXE, iSCSI, HTTPS boot. And so the thermal zone, this is just like an example reference of the thermal zone. This replaces, a whole bunch of temperature sensor drivers and the associated DT with it. So it's just a standard PMP 0C06 device. And you return the temperature in TMP, right? So the operating system is like over here, we have a pull interval, TZP, which tells it how fast it can pull the temperature. And in this case, we just are declaring an MMIO region and reading the field, calculating the millikelvin, or converting the physical analog temperature sensors return to millikelvin for the operating system. And we also are setting, I don't know, what are there, 4 or 5 temperature points for the operating system behaviors if it notices that the temperature sensor exceeds any of these values. So this is just one implementation, right? I mean, if you had a BMC or whatever handling or monitoring some of this stuff, it would be different. But this is its entirety, right? It's a half dozen lines of code, really, once you remove the comments, to add a temperature sensor for the 4 CPUs. And so we can also add active cooling to this. And so SSDTs, which are secondary tables, which DT overlays are a bit like them. Basically, they insert into the DSD names or the ACPI namespace. And so this is a similar thing where we just take over a GPIO pin and we're toggling a fan on and off as the temperature threshold is met, which you can see down here. The active cooling tripping point is configured via the firmware, and it's actually a user menu. So I don't know, I guess it's about 8 months ago at this point, a year later, 9 months, we were booting a good handful of operating systems and getting a reasonable amount of functionality out of them, right? So the OS distro installers are working. In this case, you can see VMware, CentOS, Windows 10, Fedora. And so we get back to the question about how many lines of code do we need to support this, a fan object, a couple different fans across a few operating systems. And the answer, of course, is none in the operating systems, right? Because it's ACPI. There's, I say about 25 lines of code in the firmware, which include the menus and things like that, and some basic GPIO pin configurations plus the AML to set this all up. And that's actually really what matters in the end, is that we can boot the operating systems without having to modify them, because we're conforming to the standards specified by the UEFI and ACPI committees. And these standards have been around for many years in this case. And it's also how we gain long-term support, right? This is an old picture of the PoE fans, right, which are on the RaspberryPi PoE hat. Actually work now. It's not merged to mainline. I have it in my tree, but there's another menu option here where we get variable speed fan control. And so there's no operating system change to support that PoE hat, right? It's just a couple extra lines of code here to trap to the RaspberryPi mailbox to control that fan. So in the end, how much code did we avoid putting in Linux? And the answer is a lot. If this were an ACPI only platform, it's probably about half of DT. So the ACPI Genet binding was just a few lines of code. Of course, we're leveraging the existing driver, so that's a bit of cheating. But we don't need a number of, drivers that are in the kernel, like the PCIe Broadcom set-top box, because we're doing the traditional setup, the PCI in the firmware. And there's actually two choices now. One, you either export the XHCI as a platform device so the operating system is completely unaware of the broken PCI, or in a moment I'll talk about how we've defined a PCI ECAM abstraction in the firmware for supporting non-standard PCI ECAM. And so right now, how many different PCI root drivers are there in Linux? There's a couple dozen of those as well. And overwhelmingly, they're just solving power and platform, power and clock management problems. And of course, the other big problem is non-standard ECAM regions. And so we can use an SMCC, which is a trap to the higher level firmware, to abstract this as well. And so they're like, the Raspberry Pi is one of the first platforms to support this DEN 015 specification that ARM has come up, which actually fits into the PCI specification, because it says that ECAM is only required on PCs, well, it leaves the door open for firmware supplied configuration. So that's what we're doing here, is we have a firmware interface that we have mandated, which you can, or described, which is available at that URL, which basically traps all the ECAM read and writes to the firmware. And that allows us to have a single quirk location across multiple operating systems. And it's slowly gaining ground too. We're getting, VMware and some of the BSDs have integrated support for it. And this actually fixes one of a big problem on many of these SBCs in the ARM space. So, and then there's been some DSD work. Originally DSD is supposed to be device specific, but a lot of the Linux people have been sort of merging the code using DSDs into core or common subsystems. And so there's been this discussion back and forth about whether or not it should be allowed at all. And some of the examples are, UART-based clock rates, etc. And so these are available at the following URL, and the UEFI specified ones are prefixed with UEFI dash. And so some of the problems are basically, as I mentioned earlier, not supporting standard device-specific clock and power registers, because like the RPi, it has these SDHCIs, but in order to change the card speed and voltage, you have to find another device somewhere else on the system, because the SDHCI defined ways of doing these aren't hooked up. And the other problem is when you share like user visible functionality and clock and power controllers. So you have a single like clock divisor that's, shared between, like, say, an SDHCI or an audio chip, where the user would expect to say change the audio sampling frequency, and now you don't have a way to do this without exporting the clock divisor or some firmware abstraction. And the ACPI way to get around this is DSM, but of course that tends to create some excitement because people don't really necessarily like tracking into the firmware for device specific methods, which is what DSM is. And the other big one has been because of U-boot sort of doing the minimal amount, devices are frequently not initialized properly. And so this has been like the problem with MAC addresses on a lot of network devices. They have the MAC address registers, it's just nothing has been programming them. So the standard code, which goes and reads the MAC address, gets all zeros or whatever, and then it has to source the MAC address via, DTs or some other proprietary mechanism and reprogram the registers. And this is just simply fixed by having UEFI drivers for these things, which was actually mandated by the spec for the most part. If you have the device on the platform, there's supposed to be a driver for it in the firmware. And so some quick credits. The incomplete list of Pi firmware task force contributors, which is the PFTF, Pete, Andre, Ard. You can see these people represent a number of different organizations. So this has been a community-wide effort, and it's ongoing. So, and also we'd like to thank the ARM SystemReady people who have been working on making this work across from large parts of the ecosystem. Thanks.